Okay, so last time we started talking about a little bit about some types of reactions. As we were talking about last time, there's a couple of kind of big classifications of reactions, and under those sort of classification of reactions, there's sort of other ways that you classify the same type of reaction. So we sort of started talking about last time about double displacement reactions. And double displacement reactions, again, you could kind of think of as like the big sort of umbrella of a number of different types of reactions. But in general, the double displacement has sort of this general formula as we talked about last time. And really, the one way you could recognize something as being a double displacement reaction is really what you see here on the reactant side of the arrow. And when you look on the reactant side of the arrow, what you will see is really two ionic compounds. So whenever you kind of see two ionic compounds, a positive guy, so a cation anion, a cation anion, that's usually pretty much a double displacement reaction is going to take place. And what always happens in that case is basically the two positive guys really just kind of switch partners. And what ends up happening on the product side is that we form a couple of new ionic compounds as those guys basically do switch partners. So A ends up with D, C ends up with B here, and we get some new ionic compounds that are formed over here on the product side. So again, this is sort of the big classification of reactions, which is double displacement. Within that classification of reactions that are double displacement reactions, the one we started talking about here towards the end of last time is a precipitation reaction. And a precipitation reaction is a double displacement reaction. The only sort of difference, or I got really difference, but the only thing that sort of makes it a precipitation reaction is somebody over here on the product side will end up being a solid, which is basically a precipitate that's been made. So on the product side here in a double displacement reaction, if a double displacement reaction takes place and you do form some type of solid, it can also be classified as a precipitation reaction, in addition to obviously being classified as a double displacement reaction. And that's what we'll see here in the rest of this chapter as we start talking about different types of reactions and ways to classify reactions. You can, for the exact same reaction, sort of classify perhaps it in a number of different ways, depending on sort of what you're looking at. So how do we know if, we kind of put these guys together, say these two or these two here, if we will form a sort of precipitate or not? And the answer to that really does revolve around sort of the solubility rules that we talked about. So within the solubility rules, we could use those to determine whether or not we would predict a solid to form when we sort of put together a couple of ionic compounds, or ions together, I guess is a better way of saying that. And here's again, we kind of went over them last time. If something is sort of deemed to be soluble, based on solubility rules, what that really means is everything's going to mix. You're not going to form any type of solid. And the symbol that those guys should get in a reaction is basically the aqueous symbol, as we talked about. If we determine based on solubility rules that if we put these two things together that we will get, it will be insoluble. What that basically means is they kind of don't mix. And in this application, we would expect a solid to form. And that would get a indication of a solid or S sort of symbol next to it. So here are some of these guys that we talked about last time. Basically group one and ammonium, nitrate and acetate. Pretty much if you got any of these guys in a chemical form of an ionic compound, it is going to be aqueous. And it's going to be aqueous because there's no exceptions. And because there's no exceptions, that means pretty much as soon as you see any of those guys present in a formula, you can safely put the aqueous symbol next to it because it should not form a solid in that particular case. Chloride, bromide, iodine are also going to be aqueous pretty much in every situation, except for really three situations. If any of those guys are hooked up with silver, mercury 1, or lead 2, then instead of being aqueous, as we talked about, if it is an exception in this case, it will be the opposite and would become a solid at that point. And there on the bottom there, we have sulfate, which is again soluble in everything, but there are some exceptions here. Again, silver, calcium, strontium, barium, and lead. So if you have sulfate with any of those guys, they will be the opposite of soluble, which means they will become insoluble and will get a solid. We also talked about with some solubility rules here, some things that are typically insoluble. So guys on this table on the left-hand side are typically going to make a solid. And that's our hydroxide, which will typically make a solid. But there are some exceptions. And really the exceptions that we see here on the right-hand side are really the soluble rules that we see over here on the left-hand side of this one, which basically means hydroxide will be insoluble unless it's with somebody in group 1, or ammonium, and slightly soluble here in calcium, strontium, barium. Again, slightly soluble in most people's indication usually leans a little bit towards being insoluble, but as the name implies, there is some sort of solubility. Sulfides are again typically going to be our solids, except for our kind of group 1 and ammonium exception, and some of our group 2 guys here, calcium, barium, strontium, and carbonate and phosphates typically will be insoluble again, except for our group 1 and our ammonium. So again, that sort of group 1 and ammonium being soluble in everything basically follows over here as well. So these guys are typically insoluble, will be soluble in those cases. We could use these rules to again assign our sort of states to these double displacement reactions. Again, when we look at silver nitrate in this reaction we looked at last time, as soon as we see that nitrate soluble in everything, we know it's going to be aqueous. Sodium chloride, really as soon as we see the sodium, because it's soluble in everything, we don't even need to go any further. We do know it's going to be aqueous. We could also, as we talked about last time, look at the chloride here. Chloride would be soluble in everything except for silver, lead, and mercury, which is not the case here. So again, that also tells us it's going to be soluble. When we come over here we would be looking at the chloride. Chloride, again, soluble in everything, but there are three exceptions. And again, one of the exceptions is silver, lead, and mercury 1. And in this case, that is silver. So even though chloride is normally soluble, because this is an exception, the opposite occurs, and this is an insoluble solid, and we would expect a solid to form there or precipitate. Again, coming here as sodium nitrate, as soon as we see sodium, we're pretty much done. We know it's going to be aqueous. Again, you could look at nitrate here as well, and nitrate is soluble in everything and gives you the same sort of answer. So this is how we could kind of go through our equation, our molecular equation here, to determine whether or not something is going to be soluble or insoluble using these rules. Any questions on that so far there? Now, we did talk about a couple other things, I think, as well, but a couple of things about sort of the solubility rules. We don't get too much into this, but just sort of a preview if you are taking 200B. Just because solubility rules, for example, say something is going to be a solid or something will not be a solid or whatever it may be. There are a lot of other factors that come into play when we talk about sort of solubility, things like concentration, things like pH, things like other ions that are present. All those things basically affect solubility. Even something technically, and again, you'll learn more about this in 200B, but something technically speaking that if you went to your solubility rules and said it was insoluble, although in most situations it's going to be insoluble, even things that are technically insoluble have some degree of solubility. Super, super small amount, But even something that's technically insoluble and considered insoluble, there is a small degree of some solubility there. And again, you'll learn more about that in 200B when you talk about KSP and stuff like that. But for our class, we could kind of think of them as sort of a absolute, this is exactly, it's always going to be a solid. But just a side note, in reality, even things that are technically classified as insoluble under the right situations, can have some degree of solubility and stuff like that. Now, we sort of finished up, I think, kind of talking before this about some different types of reactions and different ways that we can, or equations, different ways that we can basically display equations and sort of explain what is going on in a particular reaction. What we're looking at there on top, as we sort of talked about last time, is the molecular equation. And the molecular equation is pretty much everybody in their proper formulas, everybody together, everything obviously balanced in front. In solution, though, as we talked about, what is really going on in this reaction is a little bit different than what the molecular equation sort of indicates. And the molecular equation indicates that all these guys are kind of together. And as we talked about with our conversation about electrolytes, ionic compounds are typically strong electrolytes, which means when they go for a swim, they're really not going to stay together. So when we look at this equation, again, we could write another equation that basically explains sort of what is going on in the actual flask, beaker, test tube. And something like silver nitrate will basically 100% break apart into silver ions and nitrate ions floating around in there. Something like sodium chloride, also a strong electrolyte, will break apart into sodium ions and chloride ions. As we talked about, when you write this sort of equation like this, when you get something that is a solid, like what we see here, something that is a solid, something that is a pure liquid, something that's gas as well, if you happen to come across something like that, pretty much will stay together. Otherwise, they wouldn't be a solid. They would be free ions that are floating around. But something that's indicated as a solid means that basically those two ions came together and they kind of dropped out of solution and they're not really floating around, kind of on the bottom-ish, if you want to think about it that way. And we would keep the silver chloride here together because it is a solid. Our sodium nitrate, again, is a guy that will break apart into its ions. And this equation here that we just wrote up on top, a reminder, is what is referred to sometimes as the total ionic equation, or again, complete ionic equation. And it really does sort of adequately describe what is happening in like a beaker, a flask, a test tube. When we talk about ions that are aqueous, what we're talking about, what that really means is those are guys that are basically floating around in the solution. So in the solution, we got all these ions sort of floating around free in the solution. Anything that's a solid, you can kind of think about it as sort of on the bottom. When we write a total ionic equation, as I talked about just a second ago, we do want to always keep together things that are solid, liquid, or gas. Also, things that are considered a weak electrolyte would also stay together in the total ionic equation. So remember, we saw sort of a list of some of those weak electrolytes, and a lot of those are weak acids, for example. But when we get to our total ionic equation, like we talked about last time, we can look on both sides of the equation of the arrow, and we should be able to find ions that look exactly the same. And in this case, sodium and nitrate ions here look exactly the same on both sides of the arrow. And a reminder that that basically means that those guys are what are referred to as spectator ions. So these are our spectator ions here. And our spectator ions basically will kind of cancel each other out. They are basically just there to balance out the charge. They're really not sort of participating in forming the product. And what that leaves us after we cross out our spectator ions is a last type of equation. And this last type of equation is, again, pretty much what is left over after we get rid of our spectator ions in this particular example here. And this is what is known as the net ionic equation. And the net ionic equation is basically the equation that pretty much cuts right to the point. It is pretty much what is happening when you mix these two solutions together. And what is essentially happening is the silver from the silver nitrate, as we talked about, and really the chloride ions from the sodium chloride are going to come together. And those guys are going to come together and make a white solid. We'll pretend my blue solid here is a white solid, and it will make that silver chloride. And again, our nitrated sodium ions are they're really still there. They're really still in the solution, but they're just kind of floating around, really not doing much other than sort of keeping everything sort of balanced in the overall charge. Any questions on any of that stuff that we sort of talked about last time? Okay, so let's take a look at some here, I think. So take a second, based on solubility rules, would we expect each of these guys to be soluble or insoluble based on those rules? So take a couple of minutes here, we'll talk about it. Okay, so let's take a look here and remember that, when you're looking at an ionic compound and sort of solubility rules, you may not be able to find perhaps both things in the table or so. You may be able to find one thing, or you may be able to find both things, but at least one of them should sort of help you determine whether or not something's going to be soluble or insoluble. So remember that if you determine it is soluble, it should get that aqueous symbol. And basically what that means is they're kind of floating around as ions in a solution. If you determine something is insoluble, it should get the solid symbol, which means it's a precipitate. So either a rock hard solid, some stuff floating around, something like that in solution. So when we look here, again, just analyzing the first guy here, that is potassium, and potassium is group 1. And group 1 is pretty much soluble in everything. And there are no exceptions. So that's pretty much as far as you need to go. This guy should be soluble. This guy should be aqueous. The other thing is hydroxide. Hydroxide is insoluble in everything except for group 1 and such. So this also kind of confirms each other as well. But really, as soon as you saw the potassium, that's as far as you really need to go to determine solubility. Here again, we may not be able to find silver on the left-hand side of those tables, but we can find bromide. Bromides are soluble in everything, but there are 3 exceptions. And the 3 exceptions is basically silver, mercury 1, and lead 2. And in this case, that is definitely the exception here. So although it is normally soluble in everything except for those 3, because it is an exception, this guy would be insoluble and would be a solid in this particular case, again, because it's one of those exceptions. Any questions on that? When we look at calcium chloride, again, here we got kind of the same idea. Might not be able to find calcium, but again, can look at chloride. Chloride, much like bromide, same guy, basically. Chloride, again, soluble in everything, but just like bromide, has the same 3 exceptions. And those 3 exceptions are silver, mercury 2, and lead 2. In this particular case, calcium is not one of those 3, which means it then falls back to what we normally would expect for it. And we would expect this guy to be soluble and get the aqueous symbol. Coming here, looking at lead, may not be able to find lead on the left, but can find nitrate on the right hand or left hand side. And nitrate is pretty much soluble in everything. And there's no exceptions. So as soon as we see the nitrate, we are good to go with this being soluble and should get the aqueous symbol. And lastly here, lead 2 sulfate. Um, so with lead 2 sulfate, most sulfates are soluble. So if we look at sulfate, most of them are going to be soluble. But there are several exceptions, and lead is an exception here. And because it normally is soluble, but lead is present, which makes it sort of the exception, then the opposite occurs, and we would expect this to be insoluble and solid. Any questions on any of those, or how to use solubility rules to help us determine our solubility here? So again, solubility rules will probably be provided for you. You should have some understanding of them, and definitely have some understanding of how to use the solubility table. Um, I think that might be provided for you, but you should have some knowledge of it, I suppose, would be good. Any questions on solubility rules or anything like that? Okay. So let's again apply some of this here to our sort of double displacement reactions, precipitation reactions. So why don't you take a second here or two, a minute or two, and why don't we do this one? For this particular one, we want to write, we'll do our 3 reactions. So let's write the balanced molecular equation, the balanced total ionic equation, and the balanced net ionic equation. All right, so take a couple of minutes here. We want all 3 of those things properly written: balance, molecular, total, and net ionic equation. And again, use your solubility rules, use the idea of what double displacement is, and balancing, and see what you come up with here. Okay, let's see how we're doing. So in this case, we're given everything in words. So as we also talked about the other day as well, or a couple of days as well, um, you always want to make sure that, especially when you're dealing with equations, you're dealing with formulas, that you really do start with sort of the correct formulas. Otherwise, things will not balance so great. So here we're looking for a precipitation reaction. So automatically, we do know on the product side, we should have some type of solid because it's a precipitation reaction, which means a precipitate has been made. We are mixing aqueous solution of potassium carbonate. So potassium is K plus and carbonate is CO3 2 minus, which means when we put it together, it should be K2CO3. And we already know it is aqueous because they told us basically it's aqueous. They didn't tell us it was aqueous, but they just told us it was a solution. It would be aqueous as well. And that's how we sort of know that. Even if they didn't tell us any of that, we can use our solubility rules, and we see potassium, which is soluble in everything. So we're good to go in terms of the aqueous. And we're going to react that with an aqueous solution of nickel 2 chloride. Nickel Roman numeral 2 means nickel has a +2 charge. Chloride is a -1. So when you properly put that together, you are looking at NiCl2. Again, if they didn't tell us it was aqueous, we would know it is because we see chloride. Chloride is soluble in everything except for silver, mercury 1, and lead, and that's not the case here. So we do know that it is going to be aqueous. Now, if we were not sure sort of what type of reaction we're dealing with at this point, you can look at your 2 guys that you just wrote there, and you should be able to recognize this as an ionic compound, positive, negative. This as an ionic compound, positive and negative, which should scream to you that this is definitely a double displacement reaction taking place in this case. So what does a double displacement reaction mean? It means that we're going to swap our two positive guys. Now, this is where another thing that we talked about a number of times previously that's really important is we are not going to concern ourselves with the balancing aspect of this yet. We want to make sure that we pretty much lay up the correct formulas on our product side first and then balance it. So that is the most important thing. So to illustrate that to you, basically, this guy, basic units that make this guy up is K plus and carbonate. I don't really care. There's a 2 there at this point. It has no effect on sort of what the basic units are of this guy, which is K plus and CO3 2 minus. The basic units of this guy is Ni with a 2 plus and a Cl with a -1. Again, don't really care that much about the 2 at this point. So I'm not going to write anything crazy like Cl2 minus or anything like that, or K2 minus. That would be incorrect. Now I have the basic things that make this guy up. So I know that my potassium is then going to hook up with my chloride here, and that should give me the proper formula of KCl, not what a lot of people would write at this point, K2Cl2, because there's all those twos. So that would be incorrect. So you want to make sure that you come back to the basics here and put them together correctly, because that is potassium. I also know that that is going to be aqueous. That then leaves me really my other two guys in terms of combinations to come together, which is my nickel now will hook up with my carbonate. And again, +2 -2 tells me I really will just have one of each of those, NiCO3. And because this is a precipitation reaction and based on solubility rules here, carbonate would be insoluble in this case, and that would be our precipitate that would be made here, our nickel 2 carbonate. Any questions on that so far? Now that I have the proper equations down there on the right hand side, now I definitely should be concerned about balancing them. So again, I wasn't concerned about the balancing aspect first. I want to get the right formulas, but now that I have them, now I go back and take care of the balancing part of it by changing the coefficients that come in front of the proper formulas. And that means that we would need a 2 there. And I think that might be all we need there. So 2 potassiums, 2 chlorides, again, 1 nickel, 1 carbonate. So up here would be the correctly balanced molecular equation. Any questions on how we got to that there? So now we want our total ionic equation. So we're going to go through this and remember pretty much anything that is aqueous, that's a strong electrolyte, is going to break apart. Anything that's solid, liquid, or gas even would stay together, or something that's a weak electrolyte would stay together. In this case, potassium carbonate is a relatively strong electrolyte, so that will break apart into 2 potassium ions. So here the 2 will come to the front when we break it apart, and we will get a carbonate ion. And for our nickel 2 chloride, we will get a nickel that is +2 charge. And again, there are 2 chlorides here. So that's what the 2 really means. The 2 really means there's 2 chlorides. So the 2 would come to the front and also be aqueous. So these are really all of our ions that are floating around in that solution. In addition to over here coming to our product side, this will also break apart. 2 KCl's means you have 2 potassiums as you distribute the 2. And the 2 would also go for the chlorides as well. And now we get to our solid, which would stay together as this. This would be our total ionic equation, our complete ionic equation. And again, it really does represent sort of what is happening in sort of the beaker, the flask, the test tube, whatever it may be. Any questions on that one there? At this point, we do want to look for spectator ions, and if we properly balance it like we did, they should be exactly the same in terms of what they look like and how many you have. So if we look on the left-hand side, we got a couple potassium ions. We have a couple potassium ions. Again, as I mentioned the other day, if you happen to get to this point, you got like 2 on one side and 1 on the other side, something's not balanced right. We also will see a couple of chloride ions there, a couple of chloride ions on the other side. Again, 2 on each side because it's properly balanced. And those, again, would be our spectator ions, right? Right, like that, spectator ions. And again, we are going to cancel those guys out on both sides. And that will leave us the third type of equation that we've been talking about, which is our nickel. So our nickel with a +2 charge from our nickel 2 chloride basically goes and finds the carbonate ion that is coming from our potassium carbonate. And those two guys will come together to make a solid, which is nickel 2 carbonate. And this again is our net ionic equation. Any questions on how we got to any of those three reactions there? Again, the key here is to also make sure, that you really do balance it correctly. And again, a good way to kind of check yourself or do you understand if you did sort of balance it correctly or not is, like I said, when you get to that spectator ion sort of spot, they really should, in pretty much every situation, completely cancel out. And again, if you get to a point where they don't completely cancel out, probably something's wrong with your balancing or the way you wrote the formulas. Any questions on any of those there? Oops. Okay. Then go through here. I think they'll agree with me here. Boom, boom, boom. All right, so why don't you try these guys next here? Why don't you finish out the equation, balance it, do the molecular equation. Why don't we do all three on these as well, just for practice here. So let's do our molecular, our total ionic, and our net ionic for each of these. All right, so take a minute or two there, see what you come up with. Okay, so let's take a look and see how we're doing. So again, remember, if you're not really sure what type of reaction you're dealing with, we've only sort of talked about one big type. You could look at your left-hand side here, and again, this is an ionic compound, so that's a positive and negative guy. That's a positive and negative guy. So this is again going to tell us that this is a double displacement reaction. What that means is basically these two guys will switch partners on the other side. Again, when you are writing sort of the formulas for your products and they're not given to you, you want to do it in the order we've been talking about. So first, regardless of balancing aspect of it, we want to make sure that we put up the right formulas. So the K, which is potassium, which is group 1, so that's K plus, and nitrate, which is -1, would come together to make potassium nitrate on this side. Again, K plus and -1 from NO3 minus. The silver, which has a charge of +1, will then hook up with chloride that has a charge of -1. So +1 and -1 means we just need to put one of each of those guys together. Once we have our equations and our right formulas down, we can, at this point, look at balancing, and we see one potassium on the left, one nitrate on the left, one silver, and one chloride on the left. So it actually is balanced. We also could use our solubility rules to help us determine if we have any type of precipitate that's happening here. We see potassium nitrate, again, as we've been talking about, as soon as you see potassium, soluble in everything, so pretty much can just write the aqueous symbol next to it. Silver chloride, so we've seen this guy a couple places. Again, looking at the solubility rules, and chloride, which is soluble in everything except for 3 exceptions there. And one of the 3 exceptions is silver. So because chloride is normally soluble and silver is an exception, it is the opposite, which means this definitely will be a solid that is formed. Any questions on any part of that there? Now, for our total ionic equation, this obviously would be our molecular equation here. For our total ionic equation here, we would break this apart. So KCl is a ionic compound that will break apart into K plus and Cl minus. Silver nitrate will also break apart into silver ion and a nitrate ion that's floating around in that solution. The potassium nitrate also really in solution, not together, going to be floating around and broken apart. And our silver chloride will stay together, which is why it would make a white solid, and we would not break it apart. And this again would represent our total ionic equation. And looking at our total ionic equation, that's where we could find our spectator ions, which in this case, potassium on the left, potassium on the right, nitrate on the left, and nitrate there on the right. That being our spectator ions, which means we're going to cancel these guys out. And that is going to leave us the net ionic equation, which is silver plus chloride goes to silver chloride here. And this would be our net ionic equation here. Any questions on any of those sort of three equations, how we got them or anything like that? Now, let's say, for example, you maybe were not interested in all the other equations or just wanted to write the net ionic equation. Could you kind of shortcut it? And the answer is, yeah, you could shortcut it if you know what's going on. We know that this is the precipitate, and we know that that guy, because it's a solid, will stay together all the way through and never get canceled out, which means if we just want to kind of write our net ionic equation, we actually could start with the solid. And if you understand sort of the ions that basically make this up, you know that this is a silver ion and that is a chloride ion. And you can kind of go backwards, if you will, from the precipitate to get to your net ionic equation, without maybe having to write the total ionic equation, all that kind of stuff. So you can't sort of shortcut it and kind of go backwards, kind of the same idea as what we, kind of had over here, for example. We could have picked out the solid on this guy that we did previously and go, oh, okay, this guy is definitely going to hang out there the whole time. That is a nickel with a +2 charge. And that's a carbonate. And again, you could get right to your net ionic equation from the solid. So you can kind of work your way backwards from it, or you could go forward. And if you have to show all of them, obviously, you would want to do it forward. Any questions on any of that part there? Okay, looking at the next one here, again, if you can't recognize what type of reaction you're dealing with, that's definitely a positive negative guy. That definitely is a positive negative guy. So again, should point you in that double displacement sort of arena there. We're going to switch our partners here. Again, that means the sodium is going to come together with the chloride. We're not going to worry about balancing first. We want to get the right formulas. So again, the basic formula here is a sodium ion and a sulfide ion. Again, regardless of the two, basic unit here is a calcium ion and a chloride ion. Again, regardless of the two that is there. So when we put together the sodium and the chloride, again, really what we're putting together is Na plus and Cl minus, which should give us the proper formula of NaCl. Also means that when we put together our calcium and our sulfide, +2 and -2, should give us the proper formula of CaS in this particular case. So again, we're not going to worry about the balancing aspect of it. Once you have the formulas down, then you could worry about the balancing part. And in that case, we would put a 2 there, and that would actually balance it: 2 sodiums, 2 chlorides, 1 calcium, 1 sulfide on both sides. Any questions on that there? At this point, we could use our solubility rules to see if we got anything going on here. Sodium automatically tells us it's soluble in everything, so that is definitely going to be aqueous. Sulfur is also going to be aqueous in this case. So again, if we kind of take a peek back there at our rules, where is this? Oop, there it is. Sulfur is going to be insoluble, but calcium happens to be one of the exceptions, which means instead of being insoluble, calcium here would actually become soluble in that case. So that means if we go back to our guy here, chapter it, this guy will also then get the aqueous symbol. And this would be technically our balanced molecular equation. Any questions on that there? So you may be asking yourself, well, everybody's aqueous. I don't see a precipitate. So this is definitely not a precipitation reaction because there's no solid that's formed. So what does that mean in terms of what is going on in this reaction? Well, if we go to our total ionic equation at this point, we would end up with 2 sodium ions from here, plus a sulfide ion, plus the calcium, plus a couple of chloride ions there from here. Now coming to the other side, we would have 2 sodium ions, 2 chloride ions. Now, because this guy is also aqueous, we would get a calcium ion and a sulfide ion. And this technically would be our total ionic equation. And if we were looking for spectator ions, well, we got 2 sodiums on the left, 2 on the right. Got 1 sulfide there, 1 sulfide there, 1 calcium, 2 chlorides, 2 chlorides. Everybody cancels out, which means in reality, this would be no reaction taking place. And you wouldn't have a reaction taking place because pretty much you would have just ions floating around. Right? No precipitate made, nothing like that. And the reason this would sort of be considered no reaction is because of what we talked about yesterday as well. We talked about sort of 3 driving forces for what makes a chemical reaction take place. And those 3 driving forces for a chemical reaction to take place, one is what is referred to as an electron transfer, which is where we're going next after this. 2 is a precipitate formed, like we had here. So that's why this reaction takes place. And 3 is kind of the formation of water, which didn't happen here, didn't happen here. So here, no electron transfer, no precipitate, no water, no reaction basically took place here. Any questions on that? You basically just dump those together and have a bunch of ions floating around in the solution part. Any questions on any part of that there? Okay, so what we got left here? There's that. I think they should agree with me. That's good. No reaction. Perfect. All right, so take one more here. How about we just do the balanced molecular equation here? So take a second and write the balanced molecular equation with the states, aqueous, solid, and so forth. So see what you come up with. Okay, let's take a look here. And again, we want to approach it kind of the same way as we did before. So they basically gave us our reactants. So we'll start there. So that is ammonium sulfate. We know it's aqueous because they told us, but if they didn't tell us, again, the ammonium is soluble in everything, so that pretty much tells us it's going to be aqueous. We have our lead to acetate here, and kind of the same idea, looking at our solubility rules. If they didn't tell us, acetate again is soluble in everything as well, so we are good to go. And then here we are looking at what type of reaction. There's a lot of stuff there, but ultimately what we have is ammonium, which is a positively charged ion. We have sulfate, which is a negatively charged ion. We have lead, which is a positively charged ion, and acetate, which is a negatively charged ion. So again, positive, negative, automatically again should tilt you to a double displacement reaction. Again, here we have a lot going on, so we want to do what we've been talking about, which is we want to put together the formulas first and not worry about the balancing part until after we get the right formulas. And with that being said, what we really got going on here is the basic unit of ammonium is NH4 plus. The basic unit of sulfate is SO4 2 minus, regardless of the extra 2 that's there. The basic unit of this guy is a lead that has a +2 charge, and an acetate that has a -1 charge here. And again, we're not going to worry about the extra 2 at this point. We want to just make sure that we do put these guys together correctly. We are then going to take our ammonium and put it together with our acetate in this case. And by looking at just the basic units here, we see we just need a +1 and -1, which means we should end up with NH4 C2H3O2 as our formula. And then that would leave us our other 2 guys that would then come together. And again, looking at just the basic units here, we have a +2 and a -2. When they come together, just need one of each of those guys as well. Any questions on that so far? At this point, we can do one of 2 things, but we'll go to the balancing part. Now we're going to make sure that we are balanced, and we are not balanced. We have 1 NH4 on the right. We have 2 on the left. So to fix that, we could put a 2 in front of it. That gives us 2 NH4s. On the right-hand side, also gives us 2 acetates on the right-hand side, and that's good because we have 2 acetates over here on the left, 1 lead on the left, 1 on the right, and 1 sulfate SO4 on the left, and 1 on the right. We have now balanced this equation. Last thing that we want to do is, our sort of states. Here, looking at ammonium, soluble in everything, acetate, soluble in everything. So this guy definitely would get the aqueous symbol. Sulfate is soluble in everything except a couple of things or several things. And one of those things is when it is hooked up with lead. Lead here would be a solid. And this would then represent our properly balanced molecular equation with the states. Any questions on that? So what is really going on in this reaction? Well, what's really going on in this reaction, this is a double displacement reaction. This is a precipitation reaction. And again, if we wanted to sort of leapfrog to just a net ionic equation, we know that this guy here is going to survive all the canceling out. And it is really what is being formed in this reaction. And the 2 basic ions that come from that guy is a lead with a +2 charge, and it is a sulfate with a -2 charge. And that would be our net ionic equation. And we could figure out probably easily that it is the ammonium and the acetate here in this case that are our spectator ions. And just to quickly write it out and show you that, this would be what you would get if you did your total ionic equation. And again, here we see ammonium and we see our acetate, leaving us our lead and our sulfate to our net ionic equation. Any questions on any part of that there? So hopefully you're seeing that, as you do these, you want to make sure that you first get the right formulas, make sure you balance them. And again, you can use those solubility rules to really help you decide, what's going to be aqueous and what's going to be a solid. Any questions on any of that there? Writing molecular equations, total ionic equation, net ionic equation, using solubility rules, double displacement reactions that become precipitation reactions. Obviously, you need to be familiar with that. So again, this type of reaction, which is a precipitation reaction, is a way to classify this type of reaction. You could also classify it technically as a double displacement reaction. Again, double displacement reaction, sort of the big umbrella for which precipitation reactions sort of fall underneath. And here's one we think we saw earlier. This is our net ionic equation for lead 2 iodide. Again, that is the yellow solid that is here. And basically what is happening is the lead ion and the iodide ion are coming together to make the solid. Again, one of those driving forces for what makes a chemical reaction take place is the formation of a solid here in this particular case. All right. Now, we're going to continue here talking about double displacement reactions, but we're going to look at another sort of type of double displacement reactions. So again, the overall sort of classification, if you will, is double displacement reactions. But in this case, we're going to actually look at this other driving force for a chemical reaction, and that is here the formation of water. So this occurs when we have acid and bases that basically react together. And when we take an acid plus a base, we usually will get two things as we see on the bottom there. But we'll talk about first off, just to remind you what these guys are. I think we talked a little bit about it previously. But an acid is really something that has the ability to produce H plus ions in solution. So these are H plus ions that are basically floating around free in the solution, not attached to anything else, H plus. Are sometimes referred to as the hydronium ions. So when you talk about acid-base chemistry, H plus, which is the hydrogen ion, and H3O plus, which is a polyatomic ion, which is the hydronium ion, they are essentially the same thing. They basically represent sort of the acid part of the solution. So anything that has the ability to form H plus or H3O plus in solution is considered an acid. Well, I think as we talked about the other day as well, a base is really something that's able to produce OH minus in solution. Now, again, here what we're talking about is free OH minus, so not attached to anything, but the ability to produce that. A lot of strong bases, as we talked about, I think yesterday as well, come from group 1 and group 2 on the periodic table. They also have hydroxide actually in the formula, like sodium hydroxide, potassium hydroxide, and so forth, calcium hydroxide. But not all bases will actually have hydroxide in the formula, but they can produce it. So something like ammonia here, which is a weak base, as we talked about. And although ammonia does not have hydroxide in it, when ammonia reacts with water, it will produce something known as ammonium hydroxide, which ammonium hydroxide is a strong electrolyte and will break apart into ammonium ions and hydroxide ions. And although ammonia here does not have hydroxide in it, ultimately when it goes for a swim sort of in water, it's able to produce hydroxide, which is why it's considered a base. That's why it's considered a weak base, because it's got to go find some water and do a little bit of reaction. And that's different than if you had something like KOH. Once it goes for a swim, it's just going to break right apart into K plus and OH minus. Doesn't really need anybody to help it out with that. It's just going to kind of break apart. So this is why something like potassium hydroxide is a strong base, because it can just go in for a swim and produce hydroxide very, very quickly and pretty easily. Ammonia is more of a weaker base because it's got to do a little bit of reacting to produce that hydroxide. And by the way, this is a weak base, so we would have those arrows going in both directions, which means you're not going to produce as much of hydroxide in that particular case. Now, when we do take a reaction of a strong acid plus a strong base, it is sometimes referred to as a neutralization reaction. So if you take a strong acid plus a strong base, you get an acid and base produces a salt and water. So water obviously is H2O. And a salt is a fancy word, not sure how fancy it is, for an ionic compound, which is basically a positive and negative guy together. So it always forms that. These type of reactions where you take a strong acid and a strong base together, these are sometimes called a neutralization reaction, or an acid-base neutralization reaction. And that is because what ultimately happens when you take a strong acid and a strong base together is you will end up with basically water. The net ionic equation that will happen is basically the formation of water. So when you do this sort of combination, the net ionic equation will be basically the H plus from the acid will hook up with the OH minus from the base, and you will make water. Again, the formation of water, one of the driving forces for why chemical reactions basically take place. Also why when you do a strong acid and strong base together, it's called an acid-base neutralization reaction, because you just made water, basically. Any questions on that there? Here's a table of some strong acids and some weaker acids there on the bottom, and some strong, next one will be bases. But so here's some of our strong acids, through here. And these are some of the ones we talked about last time. In addition, we also talked about HBr being a strong acid, HI being a strong acid. Here's some of our weak acids coming this way on the bottom there. And again, these guys being more of the weak electrolytes that are going to happen. So if you have any of these strong acids in a total ionic equation, they will 100% break apart. If you got any of these weak acids in a total ionic equation, they will stay together. So you would not break these guys apart. So again, these are common sort of weak electrolytes we come across. Some of these weak acids basically will, again, remain together, while our strong guys definitely would break apart in that total ionic part of the equation. Here are some of our strong bases. Again, we talked about kind of group 1 and group 2. Here are some of those guys. And again, you can see that these guys have hydroxide in them. And that's usually a pretty good indication that you are dealing with a strong base. There's some weak bases down here, and it does have some hydroxide in it. But here's our NH3 and so forth, sodium bicarb. Again, these guys kind of would sort of stay together as well. So what really happens when we take sort of that acid and base together? Well, the reality of it is we do call this an acid-base neutralization reaction. But the reality of it is also still a double displacement reaction that's taking place. If you look at hydrochloric acid, because it's basically a strong electrolyte here, it is really an ionic compound. You could think of this as a plus and a minus. Think of this guy as a plus and a minus. Even though technically speaking, HCl are both nonmetals, acids sort of behave like ionic compounds in a sense because it gives away the H plus. So we can think of it like an ionic compound as a positive and negative guy, even though it's an H there and a hydrochloric acid for all acids. Remember, when we sort of think about acids, the cation is always H plus. So we think of it as really like an ionic compound, even though it's really non-metal. Non-metal action sort of happening, but we can't think of it that way. The question is, do you have to memorize which acids are strong, or will that stuff be given to you? It really won't be given to you probably. So I would say if that kind of list we made the other day and was on that last slide as well, if you kind of memorize those, whatever it was, 6 or 7 sort of strong acids, you could probably almost safely assume that if it's not one of those guys, then it's probably more of a weak acid. So I would say it will probably not be provided for you. You probably should have a pretty good handle on kind of those several kind of strong acids that we talked about, like nitric acid, sulfuric acid, hydrochloric acid, hydrobromic acid, hydriodic acid, and perchloric acid. So sort of those guys I just put on the list. And I think I made the list yesterday as well. So I would definitely know those guys. And probably for our class, you could probably safely assume if it's not one of those, it's probably the easiest way to sort of figure it out. If it's not one of those, then it's probably a weak acid or something like that would be the best approach. Other questions on that? Okay, what we really have going on here is this is really a double displacement reaction. And that is because if you break apart these guys into their ions, you basically have H plus and Cl minus because it is a strong acid and sodium hydroxide is a strong base. And basically our cations are switching partners. So the H plus from the acid is going to go together with our OH minus. So when you take H plus and OH minus and you put them together, that is a fancy way of writing water, basically. So that is where water comes from. Water basically comes from that H plus from the acid, OH minus from the base. And what you're left with then is the other positive guy coming together with the chloride, Na plus and Cl minus, gives us this guy, which is our salt in this case. And that's our salt in water, obviously, and Na plus and Cl minus. If we wrote our total ionic equation, Na plus would break apart from the Cl minus, and water here would stay together. It is a pure liquid, so it will basically stay together. Remember what we keep together in our, so this is our molecular equation, this is our total ionic equation. What we keep together in our total ionic equation is anything that's a weak electrolyte, a solid, a liquid, or a gas. So in this case, water would stay together. We would approach this the same way as we did with our precipitation reaction. We would go look on the left-hand side of the equation and the right-hand side of the equation, and we would look for things that are the same. We would see a chloride and a chloride. We would see a sodium and a sodium ion. Those guys, just like it was in the precipitation reaction, are spectator ions, and these spectator ions would cancel out. And that would leave us our net ionic equation of H plus OH minus, making H2O. Again, the formation of water a driving force for this chemical reaction. And always what you get in terms of net ionic equation when you take a strong acid and a strong base together. Any questions on that there? Now, like I said before, it's always what you get no matter sort of which combination of strong acid, strong base you put together. So for example, if I put together nitric acid, which is one of our strong acids, with potassium hydroxide, which is a strong base, again, positive, negative, H plus from the acid, OH minus from the base will come together to make water. K plus from the base, NO3 minus from the acid will come together to make potassium nitrate. Again, double displacement reaction occurring. If we got to our total ionic equation here, this would be H plus and NO3 minus. This was a strong base, which would be K plus and OH minus. And since I'm running out of room, I'll go underneath it. H2O on the right-hand side there, and our KNO3 would also break apart into K plus and NO3 minus. Again, here, if we look on the left-hand side of the arrow, we have a nitrate and a nitrate. We look on the left-hand side of the arrow, we have a potassium and a potassium. Those all cancel out in our spectator ions, leaving us with our net ionic equation of H plus from the acid coming together with the OH minus from the base to form water. So again, we started with different acids and bases than we did down here, but you can see that we ended up with the same net ionic equation. So under that umbrella of double displacement reactions, we have precipitation reactions like we talked about here. We also have acid-base neutralization reactions, which can be classified as acid-base neutralization reactions. They're ultimately also still double displacement reactions that are taking place. Any questions on that there? Again, here's sort of that reaction taking place. Again, our acid and our base forming our salt and water. And unlike a precipitation reaction, you know, if you looked in this sky when it's all said and done, it may visually look like, you know, there's not much that went on there, right? Unlike a precipitation reaction where you could actually see the solid here, you know, when you form water, you can't really visually sort of see it. So visually is sometimes when people miss these type of reactions in person when they're actually doing them and trying to identify sort of what is happening, because visually what's going on is, you know, not much, because, you know, when you make water, it just, you know, looks like what was there before. But, you know, so you need to understand that, you know, when you do that reaction, you know, you actually are making something, even though visually in this case, you may not visually be able to see it. So the formation of water is a really important part of sort of the driving forces for why chemical reactions sort of take place. Now, to finish up sort of our conversation about double displacement reactions and sort of overall what's sort of happening with double displacement reactions and sort of that umbrella is sometimes in a double displacement reaction, in addition to sort of precipitate being made, water being made, there's also sometimes these reactions will generate gases. And sometimes these reactions are generated, or these gases are generated directly as a result of the double displacement reaction. This is potassium sulfide and sulfuric acid. Again, positive, negative, acid over here treated like an ionic compound. The potassium will hook up with the sulfate on the other side. The H from the acid will hook up with the sulfide, and make our gas here. And this directly makes hydrogen sulfide gas. This is hydrogen sulfide gas and not hydrosulfuric acid, because the symbol here is a gas and not aqueous. So this is hydrogen sulfide gas, deadly smelly gas, which you sometimes generate in 200B experiments, but usually inside the fume. But directly here, just as a result of sort of the double displacement reaction occurring, we made a gas just as a direct product that's made. Now, sometimes this double displacement reaction will also generate a gas, but it really doesn't happen directly. It's sort of a result of the double displacement reaction happening, followed by a decomposition reaction, which is another type of reaction. So here, if we look at potassium sulfite, which is a positive negative guy, with our sulfuric acid, positive negative, again, potassium and sulfate coming together, H plus and sulfite coming together makes this guy. And this guy right here is not a gas. That is H2SO3 with the aqueous symbol. Sulfite becomes sulfurous acid, right? But the process that occurs next, and it's oftentimes very, very quick, is we have this double displacement reaction happening. But then that sulfurous acid will go through another reaction, which is known as a decomposition reaction, and basically break apart into water and SO2 gas. So this is why this is called an indirect method, because it's kind of like one reaction immediately followed by another type of reaction to generate the gas. This oftentimes occurs when you're dealing with carbonates. So for example, if you took some hydrochloric acid and like some sodium carbonate here, again, positive, negative, H plus from the acid and the carbonate will come together to make H2CO3. Sodium and the chloride will come together correctly to make sodium chloride. Put a 2 there to balance it, and maybe a 2 there to balance it as well. Now, this is again a double displacement reaction that's happening here. And you can see that no gas is generated in this case, but we do generate another sort of weak acid here, and this is carbonic acid. Carbonate becomes carbonic acid. And carbonic acid, just like the acid above, will then go very almost instantaneously through a decomposition reaction where it will form water and CO2 gas, which is, if you ever done this or sort of seen this, which probably you have, plop, plop, fizz, fizz, all that kind of stuff, you see a lot of bubbles being formed, and those bubbles are basically the CO2 gas that is being generated here. So again, this would be an example of an indirect gas production as a result of a double displacement reaction followed by a decomposition reaction. Any questions on that there? Okay, so we just got a couple of slides here to finish up this whole topic. So we're going to finish it, and then we'll lay it up here for today. So again, visually, this case, you actually would see something visually happen here. You would see a bunch of bubbles basically forming. Yeah, we're actually going to see a table here in just a second that might answer your question about sort of when a decomposition reaction occurs in this sort of application. So hopefully that'll answer it in just 1 second. But again, here you definitely will see those bubbles form, and that is the CO2 gas that's being generated. And again, this is sodium bicarbonate, like baking soda, and hydrochloric acid. And again, it is the sodium and the chloride coming together to make our sodium chloride, which is what we see here. It is our bicarbonate and our H plus coming together, which makes carbonic acid like I did on the previous slide. And that carbonic acid again goes through that decomposition reaction and produces pretty instantly CO2 and water. And again, that's all the bubbling and stuff that you do see is that CO2 that's being sort of generated. So how do you know sort of this is going to be a sort of direct formation of a gas or an indirect formation of gas in these double displacement reactions? Here's a nice little table that sort of summarizes, when you would expect those situations to occur. If you have, in terms of a reactant, some type of metal that contains sulfur or some type of metal that contains HS minus in it, and you react it with an acid, you will directly form hydrogen sulfide gas. So if you look back on this one right here, a metal with sulfur, which is what we have here. So that's what the first column says. This is a metal, right, with sulfide or sulfur, and it reacts with an acid. We produce H2S directly. So that's sort of what that first sort of column means. If you have a metal that has carbonate or a metal that has hydrogen carbonate with it, and you react it with an acid, you will produce carbonic acid, which will go through a decomposition. And the ultimate gas that you'll end up with is CO2. And that's what we saw here. We had a metal with hydrogen carbonate and an acid. So that's what the first two columns there mean. Metal, hydrogen carbonate, and an acid forms this, which then will break apart into our CO2. And also this one that I wrote over here, this is a metal with carbonate and an acid, again, forms our carbonic acid through the double displacement reaction and ultimately forms that CO2 gas that's basically there. If you have a metal that is hooked up with sulfite or a metal that's hooked up with hydrogen sulfide, basically, and you react it with an acid, you will get that H2SO3, the sulfurous acid, and that is the one that we saw here. That's a metal with sulfite hooked up with an acid, going to make a sulfurous acid, which, as we saw, will then break apart into basically our SO2 gas that's going to form. So again, a decomposition reaction happens right afterwards. And lastly, if you have ammonium and you react it with a base, you will make ammonium hydroxide, and it will go through a decomposition reaction to make ammonia. And I think there's an example here. So here's ammonium with a chloride reacted with potassium hydroxide will generate our NH3 gas. So this is a nice table that sort of explains a lot of those double displacement reactions. But in each of these cases, these really are double displacement reactions, are double displacement reactions followed by a decomposition reaction, and a decomposition reaction, which is really more of a redox reaction, but it basically is, as we'll talk about next time, when you take one thing and break it apart into two or more things. And that's essentially what we're doing here. We're taking one thing, breaking it apart into CO2 and water, taking one thing, breaking it apart into SO2 and water, and taking one thing, breaking it apart into NH3 and water as well. So in these sort of gas generating reactions, sort of indirectly, it's basically kind of a twofer reaction, double displacement followed by decomposition. And again, a decomposition is actually, again, a redox reaction, not really under the umbrella of double displacement reactions. Any questions on that there? Now, to wrap up this with double displacement talks, just so we're clear, let me go, which way? We'll go back maybe. Go this way. So in terms of double displacement reactions, which again is our AB plus CD. Underneath this big classification of reactions, we have seen that you could also classify these as precipitation reactions. You could also classify this as a acid-base neutralization reaction. And really underneath here, you could have some that will produce some gases. So these are sort of three different classifications that really are sort of the same thing. So again, the big classifications, double displacement reactions, which for all these reactions that we've seen up until this point, you could classify every single one of them really as a double displacement reaction. In addition to all the reactions that we saw that form some type of solid or precipitate, in addition to classifying that reaction as a double displacement reaction, you could classify that reaction as a precipitation reaction. And those acid-base reactions that formed water, in addition to classifying them as an acid-base reaction, they could also be classified as a double displacement reaction. So again, double displacement reaction, kind of the big umbrella, and underneath that, two big categories for those is a precipitation reaction and an acid-base reaction or acid-base neutralization reaction, which they both are double displacement reactions, but can be classified in different ways. And as I mentioned earlier, again, you can classify the same reaction in a couple different ways depending on what you're looking at. And to finish up here, these two sort of sub-classifications of reactions, one you make a precipitate, one you make water. And again, these are two of the three really driving forces for why when we put things together, chemical reactions take place is, again, we want to make a solid, we want to make water, or we want to transfer electrons. Those are really the three big, this is why a reaction sort of takes place. Any questions on any of that there? Okay, so that we will lay it up there. That should take care of double displacement reactions, which